So if I look at, really fundamentally here, the tangential velocity of one tooth, gear 1, and meshing tooth on gear 2, those velocities have to be what?
Same.
The same. Right? Angular velocity to linear velocity relationship is what? Okay, 1 times the radius is equal to that velocity. And for omega 2, it has to be minus because of the direction. And what do we know about radius and number of teeth relationships for gears? Well, for properly measured gears, what has to be true about the 2 gears? What?
The ratio of the gear should be the same.
Ratio, meaning the number of teeth between those? What do we know about the relationship between teeth of each gear? The teeth have to be the same size. What does that mean? When you choose gears, what are you looking for? The pitch, diametral pitch. What diametral pitch? What diametral pitch? Stuff you have to look at when you choose gears. You know, there's nothing to gear ratio. What is diametral pitch? You say it's a 24 pitch gear. Let's see what we can tell. 96 pitch gear. So what does that mean? It's number of teeth of what? Unit diameter of the pitch circle. What's a pitch circle?
Circle where they touch.
Yeah, this tangential circle, circle, the tangent of the touching gear. So halfway between the teeth, not reflecting. Now, what I've drawn here is really on the pitch surface. This is the part that's tangent. So the diametral pitch has to be the same in each gear. In SI units, it's not diametral pitch, it is what? Modular. It's modular. Essentially the same type of thing. So instead of the number of teeth per unit diameter, it's the inverse of that. It's the distance of the tooth from tooth distance. They have to be the same. What we're saying is your teeth have to be the same. All right. So what's that say about I can replace R1 and R2 with what? These things is really nasty to learn here. But I can replace this one very simple. Let's do that. Know this stuff. You know this stuff. All right. It's a job interview. I also just lost the job. Mechanical engineers. This is stuff you should just know. I won't say radius, but I put in number of teeth. Number of teeth. Thank you. In terms of number of teeth, right? That's just stuff. Don't never seen that before. Right, so say so. So, relationship. Minus, this one's matter. Irration. It's negative because it's directly changing. Okay, let's look at torques. What do we know about the teeth in terms of the torque? Force of one tooth onto the other tooth must be equal to the other tooth's force acting on this. It's in equilibrium here. All right? So the forces, F1, support the force relationship is what? Equal, right? Again, I'm going to replace the radius with number t. Got that. So, notice the relationships here. Omega 1 and omega 2, and T1 and T2, right? One case it's minus N2 over N1, the other case is N1 over N2. How do you describe that?
The inverse relationship?
Inverse, it's a negative reciprocal, as a matter of fact, right? The negative reciprocal. That's always going to be the case. It's torque times the speed, right? One times the middle is power. Here one. Let's replace these relationships here. So, said this 100% efficient, this is what? Power in year one must be equal to power in year two. That's the case. Now let's check. Well, you just replace omega 1. I have N2 over N1 minus that here. And T2, N1, N2, which is equal to T to omega 2. Minus sign means I'm just going the opposite direction. Okay? So, power in equals power out. Okay. Makes sense? So this is a transducer. It's converting mechanical energy of one form, some torque-speed relationship, to a different one. Right? All right, make sense for this? Look at an electric motor. And I'm going to stick with DC because they're a little bit simpler. Brush DC motors, permanent magnet motors. Thanks to that, permanent magnet DC motors, you have the same straight line relationship. On the electrical side, we have, well, voltage and current. Right? Mechanical side, we have speed and torque. Right? And you want to remember the relationship between the electrical properties and the parameters in the mechanical parameters for a DC motor. We have two things that apply together. Back EMF and the torque constant. Right? We have a back EMF. And I'll use case B for that and a torque constant. If you look up motors, one of the things they'll state the manufacturers what the backing electrons and the torque constant are. All right, so what are these relationships? How do these relationships work? Or the backing electrons, what's that related?
Voltage and speed.
Voltage and speed, all right? Remember that relationship? No, you close?
K times omega.
All right, well, the voltage is equal to what? KE times omega. What are the units of KE? Well, they've got to be units of what? Voltage over radian seconds. Volt seconds. All right. How about torque? Remember that one? E is equal to torque constant times the current. So the dimensions of torque constant are torque over current. Okay. Now, if I have a perfect motor, perfect efficiency, power in must be power out. Well, power from electrical is what? And power from mechanical, and speed. Right? Now look at this. So voltage, let's say voltage is equal to KE times omega, and current, let's put it in this form, torque over KT, or this is KE over KT. And what's that say about KE over KT? What's the what?
They're the same.
They're the same. And numerically they are if what?
You know the right units?
In the right units. And those right units are, what are the right units?
That's volt seconds.
Well, SI units. The wrong units are the English American standards. All right? So if you get lawyers, a lot of times you do this in this country, torque is often listed in ounce inches. Things, speed is almost always what when you look at the catalog.
RPMs.
RPM. Are those SI units? No. You need to convert radians to seconds, Newton meters, and it works out very nicely. All right? Otherwise, you need conversion factors. Right? All right. Questions? Does that make sense? So let's see how we can use these for modeling. I want to be able to model a system, electrical, mechanical, whatever, without having to solve, well, here's solve the electrical part, then I'm going to solve the mechanical part, then I'm going to do lighting. I'm going to solve it in one shot. Okay? So, let's look first at some gears and see some problems we have. Here's model. Gear 1, 2, torque. That. Okay. So here's our system. How many different speeds do we have? 2. 2 plus OS. We need OS to do.
Oh, round 3.
3. And I'll make everything same direction. Plus that. Okay, so let's do a linear graph of this and see what, well, let's just solve it first of all. Let's do brute force solve. What's the relationship between omega 1 and omega 2? T's and 1. 32, 2. 2, 1, T, 1. Do that right? Now, we have this torque source here, right? Acting on J1. So can we sum all of the torque on J1? What would that be? Who is the hardware right now? Which was easy, right? So let's figure out a diagram on J1. Yeah, pi torque T. What else? The torque is here, right? It's going to be close. So I have T minus all this T1 equals M J omega 1 dot. And T1 is what? Well, this, should write it this way anyway. Right. What's T2? Write it down. Well, it's going to be essentially torque acting on this mass. This way. And what's the relationship between T2 acting on J2? Can you do a pretty bad diagram with this? What is T2, this is torque acting on it. J2 times omega 2 dot. Yeah.
I think the conversion from T2 to T1, we have the ends flipped. Something small.
Can I get a reverse?
Right.
Oh, you're right. You're right. I have it right here and then just copy it right here. Oh, sorry. Just copy down exactly right here. Okay. What about the relationship between omega 1 and omega 2? In this case, I have, well, I can put this in here. This is J2, omega 2 dot. Dots. Okay. Substitute in. And everything on the other side.
Should be.
And I'm trying to reverse the same kind of thing. Sorry. Carrying my error right on through. Let's get that right. Times J2 omega 2 dot. All right, did I get that right? Nope. And then omega 1 and omega 2.